Good morning, everyone. Thank you for making it to this talk, and welcome. Feel free to settle in, take your time to find a good seat for you. Meanwhile, I'm going to introduce myself. I'm Manuel Vivo. I'm a staff mobile architect and Android engineer at Bamboo Link. And today, I would like to talk about how to collect like a pro. So it's going to be a deep dive on the Lifecycle-aware coroutines APIs. And a little bit of a disclaimer before I start. So the content of this talk is some of the work that I did while I was at Google a few years ago, and not directly related to the work that I'm doing at Bumble. But if you paid a little bit of attention, you notice that I removed the Android from the title. And this is because if it was originally, the APIs were created originally for Android, in reality, nowadays are Kotlin multi-platform compatible. So even if you're not an Android engineer, you should be able to follow the talk very easily and then apply this knowledge to your projects. So the agenda for today is that we're going to start with some flow essentials, one-on-one on flows, so that everyone is on the same page and everyone can follow along throughout the rest of the talk. Then we're going to introduce the resource waste problem. And this kind of appears if we don't collect properly from the UI. We'll see that in a second. And then to kind of mitigate these problems of wasting resources of the device, we're going to introduce the Lifecycle-aware APIs. And then we're going to look at the implementation details. Here, we're going to be looking at some low-level APIs that we're going to be using. And then we're going to learn a few things along the way. I think it's going to be pretty cool. And lastly, we're going to see how to create, build good Kotlin coroutines APIs, whether they are public-facing, like the Lifecycle-aware ones, or you are simply creating some utilities in your company. We should be paying attention to some good practices. Just to show a counterexample of something that we ended up shipping in the early versions of Alpha, we'll see what's a not so good example looks like as well. So let's get started. Flow essentials. Again, when we talk about Kotlin flows, we are talking about streams of data. And this is pretty much applicable to any other streams of data solutions that you can find out there. So whether you are coming from iOS and you are using async stream in Swift, or maybe some Rx library, RxJava, or Rx Swift as well, you will see some of the concepts are very similar, and you can apply what you learned into your own solution. And probably the best introduction of Kotlin flows that I did in my life was this talk at Android Dev Summit 2021, Kotlin flows in practice with José Alcerreca. So if you haven't watched it, I fully recommend it. If you watched it, probably you remember this lovely avatar Pancho that was trying to get some water from a particular lake. And then he was trying to construct some pipes, aka flows, and then with some colors, aka flow operators, to try to get the water to their place in the way that he needed it. And also, we were mentioning that sometimes you don't even need to care about creating flows, because those flows are provided by you out of the box by some of the common libraries that we use pretty much every day, right? Data sources like Retrofit, Room, Work Manager, they already provide flows that you can use in your project. Also, we saw how data flows in a typical application hierarchy. This is more or less common in pretty much all mobile applications. You can maybe skip some of the layers, but typically it's something like this. And then if you follow unidirectional data flow, you will see that flow data goes into that particular direction. And we typically expose flows. And lastly, in the last layer before the UI, we could expose probably a state flow, an observable data holder, because the UI always needs some information to display on the screen. So whether you're using ViewModel or just a generic state holder, usually this is kind of the APIs that you are using in your project. OK, so coming back to our presentation, we're going to be very fast talking about the differences between cold and hot flows, because we will need that knowledge a little bit later. You probably know this already. The cold flow is going to produce data when it's actively collected, and it's going to start fresh for every single collector that collects the data. And a good way to create a flow is with the flow API builder. And just very simple, we create a flow, we emit 3 items, and then we close the flow, like there is nothing else. If we keep using the same water analogy, this is like opening the tap, right? Like if you're at home and you want to get a new stream of water or data, you just open it, right? And then if the tap is closed, if no one is there, like using the tap, then no water flows at all. So the same happens with cold flows. As opposed to this, we have hot flows, which are going to be continuously emitting data regardless of collectors. So collectors are going to be jumping into the existing stream, and depending on how the hot flow is configured, they could see an item or not. Just a simple API to create that hot flow. It could be the mutable shared flow, and then you emit an item. Whoever is there is going to get it. If no one is there listening, nothing happens, right? It's following the analogy. Here we have a river. If you want to start observing items or collecting them, you get there to the bank of the river, and you can see the items that are flowing. Very quickly, sometimes most of the flows that are created are cold. It could happen with the flow API builder, as we saw, or maybe like other operators like flowOff, asFlow. These are extension functions that you have normally in collections that you can use. And then we have, for hot flows, the shared flow and state flow APIs. And then if you want to convert a cold flow into a hot one, you can use the sharing or stating. Back to our application. Is it hot or cold? Like whatever we receive from the previous layer. Well, in reality, like you don't really know, right? Unless you go there to the implementation details. But the thing is, you don't really need to care. Even in the view model, you could think, OK, I'm exposing a state flow. But you don't even know how that state flow is constructed, right? Maybe it's using the stating operator, and then it's canceling the upstream flow collections if there is no one there. Like it can get a little bit tricky. And the TLDR is that you don't really care, and you just simply need to do the right thing, air quotes, in every layer of your application. If every layer is responsible for doing the right thing, then we shouldn't need to worry about. And then this talk is going to be mainly about the UI layer, how to collect flows properly from here. And this is a spoiler alert. We'll see this kind of evolving, making sense throughout the presentation. But the good thing, or the right thing to do in the UI layer, is to stop collecting flows if the application is in the background, if the user is not actually looking at the screen. And with this, we're going to introduce the resource waste problem, how if we don't collect properly from the UI, we will see that our app is consuming more resources, like it could be CPU, memory, and ultimately it's going to potentially drain the battery of the device. And we don't want users to experience that. And when we talk about the resource waste problem, we have to slightly introduce the typical UI lifecycle. So this is for Android, but also applicable to Kotlin multi-platform, as I was mentioning. The UI can go through these different states. Here, the light yellow here represents when the UI is visible on the screen. Whenever the UI is at least started, the UI is going to be there. It doesn't mean that it's going to be foregrounded, because that's probably when it's resumed, but at least the user can see the UI. And then when it falls below started, when it goes on stop, then the UI is not going to be there. OK, keeping this in mind, a quick refresher on that. The use case that we are going to be looking at is a typical maps application, where we are going to see where the user is located, and we're going to be updating it. So the updates could happen from these location updates that the view model exposes. Again, we don't know how that's constructed. We don't care. We just need to do the right thing. I mean, if you see this code in a typical code review, you might think, OK, this is OK. It's creating a coroutine in onCreate. That's OK. Why not? It's collecting, and then it's updating the UI on the screen. OK, all good. But then you can say, OK, I'm not using Android. I'm not using these APIs. I'm using like full-on Jetpack Compose. The thing is, If you use the collectASState extension function to produce state, this is actually doing the same. So when the composition is added usually in onCreate, and when this composable is added to the composition, it's going to start collecting from the flow in onCreate. So even if you are using compose and you're using collectASState, you are suffering from the same issues. So there we go. Here we have our maps application. The user is interacting with the app, and they are moving along. So every time that we are going to get a new location update from our GPS provider or data source, we are going to be updating the UI and moving the position on the map. Right? This is quite easy. Here we can see the line. The application is foregrounded. Means the user could potentially be interacting with that. But at some point, he might close the app, or maybe they are getting a phone call or something, and then the application moves to the background. And if it's in the background, means it's still running. The user didn't fully close the app. And because of the way we were collecting the flow, it feels it's still getting consuming resources, right? It's getting location updates in the background. And that's wasting the device resources, right? The GPS provider is still emitting signal. We are collecting from it, even if we don't care that much. And potentially, this could be running for minutes, maybe until the user decides, hey, what's happening here? And this not only wastes resources, but also it could be dangerous depending on the UI toolkit that you are using. For example, with Android views, if you attempt to update some of the UI while the application is in the background, it could potentially crash the app. I believe this doesn't happen with Compose, but still, it's not a great experience. So coming back to what we were saying earlier, the expected behavior in the UI is to stop collecting if the app is in the background. OK, how can we do that instead? So a way to mitigate this, if we don't know about any other APIs, what we could do is manually start collecting on start of the activity and then cancel that running coroutine on stop. And this is OK, right? But this could get a little bit annoying because you have to do this every time. If we want to replicate this in the fragment, it's even a little bit uglier, right? Because now you have to access the view lifecycle owner, not the lifecycle owner, and then add the observer, and things get more complicated. And I didn't want to even show what you have to do in Jetpack Compose, because you cannot even use collectASState. It gets a little bit messier. But thankfully, at Google, we created the Lifecycle-aware coroutines APIs that is actually supposed to make the experience much more enjoyable for the developer. And we're going to introduce different APIs here. So we have a couple of them, part of the Lifecycle runtime KDX artifact. We have repeatOnLifecycle, which is an extension function on both Lifecycle and Lifecycle owner. Then we have the flow operator, flowWithLifecycle, which is going to be doing something very similar in a different setting if you need it. And then in Jetpack Compose, we have the collectAsStateWithLifecycle, which is also an extension function on both state flow and flow. And you can see that here, all of these APIs are Kotlin multi-platform compatible. There is a small caveat here in the collectAsStateWithLifecycle that I will tell you in a second. So if we start with repeatOnLifecycle, you'll see this is a suspend function. That means it needs to be executed within a coroutine, and it's going to receive a state and a block of suspend code, right? A suspend lambda. And repeatOnLifecycle, what's going to do? It's going to create a coroutine internally, and it's going to run this block, suspend block, every time that the lifecycle goes into that particular state. And then it's going to cancel that running coroutine when the lifecycle falls below that particular state. So what we have here is kind of a restarting behavior that every time the lifecycle is at that particular state, block is going to be executing. Because it's a suspend function, at some point, it needs to resume the execution of the calling coroutine, and that's going to happen when the lifecycle is destroyed. And we'll see that in a second. So how can we use this API? we can, for example, we can grab the collect call that we had earlier in the repeatOnLifecycle, and we can pass in the started state. And what's going to happen here is that the collect lambda is going to be only executed only when the life cycle is at least started, right? So here we have the impression that, or actually the solution that we only collect when the life cycle is at least started. If we pass in the resumed state instead, it's only going to do that while the application is fully foregrounded there. It's going to be doing that. It's going to stop collecting when it goes on pause. So back to our code. What we do is that right now we have the same exact code as we started at the beginning, but we grab the collect call with the repeatOnLifecycle. And then in the fragment, instead of the code that we saw earlier with the viewLifecycle-owner, here we simply create a coroutine called repeatOnLifecycle with the viewLifecycle-owner, and then we collect. That's pretty much it. And as I was saying earlier, something to keep in mind is that when repeatOnLifecycle resumes, you could still be doing things as part of this coroutine, but be careful because the lifecycle is destroyed. So don't attempt to update any UIs or do nothing with that. The other API that we have is the flowWithLifecycle. This is a flow operator, and it's going to behave pretty much in a very similar way. So we are going to pass in a lifecycle and then the min active state. And what's going to do is that it's going to start collecting from the upstream flow when the lifecycle is at least in that min active state, and it's going to cancel the collection when it falls below that. And then it's going to emit the items to the downstream flow when the lifecycle is at that particular state. How we could use this API, very similar, location updates, flowWithLifecycle, and then we can collect. By default, it's going to receive the started state, because that's kind of pretty much the recommendation. But if you, for some reason, want to do it in the resume state, it's going to follow pretty much the same behavior that we've seen. How we can call this in the activity, very similar. You can launch the coroutine, call flowWithLifecycle. It's just the same behavior, but in a slightly different way. And lastly, the other API that is available in Jetpack Compose is the collectAsStateWithLifecycle. The function signature that we see here is the one which is the extension function on flow, but you also have it with the state flow, and then you don't need to pass in the initial value because it's going to get the state flow dot value, the current value. We pass in the lifecycle owner, the min active state, and then a potential or optional context of a coroutine context in case you are interested. And what it returns is state. And this is the compose state that is going to tell the state engine to recompose part of the composable function if there is a new value. And then all the functions that are, or like the recomposing subscopes that are reading that particular value is going to be recomposing. How do we use this in our code? Similar as before, but instead of using collectAsState, we are going to use collectAsStateWithLifecycle. And then states are only going to be updated only when the lifecycle is at least started. So we are going to get that behavior for free just with one line of code. And earlier, I said that this API, collectAsStateWithLifecycle, is kind of KMP, Kotlin multi-platform compatible with a caveat. And this is because you need to import the JetBrains version of Lifecycle runtime in Compose. And if you want to see these APIs in action, you can see the project from John O'Reilly. It's over there. Thank you for coming. Confetti, People in Space. These are like great Kotlin multi-platform examples that are following the best practices. OK, so we have these three different APIs that we just saw. If we zoom out a little bit, we will see like when can we use that, right? Like, we introduced different types of flows earlier. Do we need to use these APIs all the time? We said that by default, yeah, because like we have to do what's right for our layer. But how do they affect each one? If we think about hot flows, we don't really care, right? They're going to be running all the time. It doesn't really matter. So, OK, but it's a no-brainer. Like, we use them. Like, we are used to this. We don't know if it's a hot flow or not. But yeah, that's all good. Then cold flows, like, sure, as well. Like, there are some cold flows that actually, it depends on how you do it. You can use other APIs to try to suspend the collection. For example, like Android provides some APIs, like when started or when resumed, that even if you don't use these APIs, you can kind of get by, because if you suspend the collection, the cold flow is actually because of the what we were talking earlier about the back pressure. It's when you call emit is actually gonna wait for the item to be collected. If it's not collected, then you are not actually wasting resources. So sometimes cold flows could be okay if you use other APIs. But when there is no way to escape, if you have cold flows that are backed by a channel or a buffer. And you might think, okay, that's not that very common, right? It really is, right? If you use operators like conflate or flowOn, which is very popular, you are going to get this behavior. And there is no way to escape if you don't use these APIs. So yeah, zooming out, that's why we kind of gave the introduction of cold and hot flows. TLDR, use them all the time, right? It's a no-brainer. It's quite easy to use. The developer experience is pretty nice. So we zoomed out a little bit. Now we're going to zoom in. We're going to look at the implementation details of those APIs. We're going to be looking at some low-level coroutine APIs as well, and how or when they are useful to use them in our projects. We will see, like, every single API that we introduced, it uses a low-level coroutine API under the hood. We have suspend cancelable coroutine, callback flow, and previous state. We're going to do a small introduction to these APIs, and we're going to see how we are using them in these APIs to get the benefits that we get from them. We start with suspend cancelable coroutine. This is an API that is going to allow us to jump into the coroutines world and create a suspend function. So for example, a very typical use case is you have a callback-based API, and then you can make it sequential with coroutines. And the good thing about this particular API is that it's going to leverage automatically the structured concurrency from Kotlin coroutines, right? So it's going to propagate errors properly, and the cancellation is also going to be propagated as expected. So let's forget about the water analogy. Let's do something like more conference-driven. Let's the coffee. And here, imagine what we have a coffee callback API that we want to use in coroutines, and we want to make it more idiomatic. So here we are Starbucks, for example. They don't pay me, but I like it. And then when we prepare or when we order a coffee, then we are going to wait for the barista to prepare it and grab it, right? And that's a callback API. So we want to convert this to a suspend function instead. So what we are going to do is suspend function, prepare coffee, and then we call the suspend cancelable coroutine API with what we are returning, type coffee in this case. And here we get the continuation. Probably, if you're familiar with coroutines, you are tired of hearing about continuations. But this is actually what's giving us control of what to do with the calling coroutine, right? This is giving the opportunity to be able to resume the coroutine whenever we want, or to return an error, or maybe just wait for cancellation signals. So whenever the coffee is ready and we get the call back from prepare coffee, we can do continuation. Hey, I want to resume the execution of the coroutine, and I'm going to give the fresh coffee. I'm going to return it. You can return a value. You can return an error. And then if still the coffee wasn't ready, and then the calling coroutine is getting canceled, you have this function on continuation, invoke on cancellation, that here you're going to get the call back whenever, in case you need to do some cleanup. In this case, we want to cancel the order because we are running out of time and we need to leave. How do we call the prepare coffee API? We create a suspend function, right? Need to be executed in a coroutine. We create a coroutine with a launch, and then we call prepare coffee. And now we remove all the callback-based APIs. We remove all the nested functions, and we simply sequentially wait for our coffee to be ready, and then we drink it. How are we using suspend cancelable coroutine in repeatOnLifecycle? Well, It's going to be a long code, FYI, but we're going to digest it and we're going to be able to understand what's happening very easily. So we're going to call suspend cancelable coroutine, right? It's a suspend function, and here is what we're doing with that. We get access to the continuation, and because we want to be listening for the lifecycle events, right? We're going to be creating this restarting behavior with coroutines. We're going to be adding this observer to our lifecycle that we get as part of the extension function. We call the add observer. Okay, what do we do inside the observer? We mentioned earlier that if we get the onDestroy event, we are going to resume the coroutine. This is what we do, continuation.resume. We don't return anything. Unit, there is nothing to communicate back, just that we finished doing our stuff. What else? So we're going to be here defining when do we need to start the work, the coroutine with the block, and when do we have to cancel it. So if we get the event of canceling the work, then we're going to cancel the ongoing coroutine. And the ongoing coroutine is being held here in the launched job parameter that is defined somewhere else. We're going to cancel the ongoing coroutine. We're going to set it to null, and that's it. But now, if we get the start work event, this is now when we need to start the block of suspend lambda, right? So we're going to assign the launch job. We're going to call this coroutine scope.launch. We are going to create a new coroutine. I'll explain in a second where that coroutine scope is coming from. What you expect now, we call block, right? And this is pretty much what we are doing with a few niceties on top of it. So we're calling block, right? And then we are adding a coroutine scope and then a mutex. Let me explain. So the reason why we are grabbing block inside a coroutine scope is because in block, in a suspend function, you can create more coroutines inside it, right? Coroutine scope here is making sure that all the coroutines that have been created are weighted, right? So we're going to wait for all of them to finish before we actually carry on with the execution. And then we create a mutex, and when we use the with lock, because it could potentially happen that if lifecycle and the state goes in and out of that particular state very rapidly, we could face race conditions. So just as a safety measure to avoid race conditions and asynchronous problems, we are going to be safe and grab it with a lock. Okay, so that's pretty much it. And then the pending question was, where is this coroutine scope coming from? And that comes from somewhere else because suspend cancelable coroutine is executed here in the middle, and that's grabbed in more complicated code. It's not that complicated. So coroutine scope is called when we call this the repeatOnLifecycle function. And why do we did that? We did that because coroutine scope is preserving the calling context. It's preserving the context where the repeatOnLifecycle has been called. And we have to preserve that context because we need to move to the main dispatcher because we need to add and remove observers from the lifecycle. So we use this nice trick we call coroutine scope so that later, buried down the code of our function, we can actually use the same context where the repeatOnLifecycle was originally called. Okay. What else? So we grab the suspend cancelable coroutine code that we saw in a try, so that we can finally, if in case repeatOnLifecycle, the coroutine that call it gets canceled, then we can do some cleanup. In this case, again, we cancel the ongoing, the repeating coroutine that is happening there, and then we remove our observer from the lifecycle. It wasn't that scary. It was a long code snippet, but everything makes sense, right? Callback flow. This is the other API that we are using under the hood for the flowWithLifecycle API. And what it's going to do is pretty much convert any other stream of data solution that you can think of into a Kotlin flow. So here we're going to be using callback-based APIs, which calling back with multiple data multiple times. And the nice thing as well about this API is that it can handle back pressure. So if the consumer is slow, the events are going to wait. This is what we were telling earlier at the beginning. So here we have the callback API, slightly different. Now we have listen. We want to listen to all the orders that the barista is preparing, not just ours. And if we wanted to convert this and have all the elements in a flow, what we can do is create a function, coffee orders, for example. We expose a flow of type coffee order. We call callback flow, and here we are, callback flow is internally going to create a coroutine, although we don't care about it right now. We'll see that in a second. Inside it, we are going to call listen, and then every time that the barista prepares a coffee, what we can do is call try send. This is a function we can use in the callback flow context. And then this is emitting an item into the flow from a non-coroutine, non-suspend function, right? Because the callback is not a suspend function. What we can do is, because we want to get all those items and never stop, is that at some point, if the flow is canceled, if the collector stops collecting, then we can call await close to wait for to actually wait for the flow to stop finishing, and then we stop listening to our barista. How we can use this in our code? We create a coroutine, coffee orders, we collect from this, and then if the order is on my name, then I'm gonna drink it. I hope many manuals are in Starbucks and I can drink a lot of coffee. And then lastly, also, how are we using flow with lifecycle, right? How are we using callback flow inside this function? So normally, very straight away, we call callback flow straight away. And here we can do repeat on lifecycle, right? Like we have already the restarting behavior that we wanted. So we are going to use that functionality that is being already created with the min active state that we are passing with the parameter. We collect inside it, and now because callback flow, as I was mentioning earlier, it creates a new coroutine. We are in a coroutine context. Instead of calling try send, we can call send directly in the flow. That is going to kind of respect the back pressure in case the consumer is low. Because repeat on lifecycle is going to resume the execution of this coroutine when the lifecycle is destroyed. Last thing we need to do in the callback flow is just close it. Like there are no more items that are going to be sent. We close the callback, the flow, and that's pretty much it. And then the other API that we're going to be using is produce state, and this is a Jetpack Compose API that is going to allow us to bridge the synchronous code that we might be having in coroutines into Jetpack Compose's reactive state model. This is going to tell the engine to recompose whenever we are reading a particular value, state value. And then it's nice because it's going to reduce boilerplate. It's going to automatically create a coroutine in the scope of the composition, and it's going to simplify a few things for us. How this API works is that when you call produce state, you're going to be in the context of a coroutine. It creates a coroutine, and every time that you set a new value, it's going to cause that recomposition that we are expecting. How do we use produce state inside the collectAsStateWithLifecycle? Again, very, very similar to what we've been doing so far. So we are going to call produce state. We are returning the state produced inside. And then we are passing all the parameters that we are getting to the produce state. And this is what I'm going to do, is that if any of these parameters change at the calling side, it's going to restart, right? We got a new value. We need to restart the lambda that we got here. Very similarly, we are going to call repeat on lifecycle, min active state. This is only going to be executed when the lifecycle is at least at that particular state. And then we collect from the flow that we have an extension function on. What do we do with those items that we get from the flow? We just assign the produce state value to it, and that's it, right? Also, the composable function is only going to recompose when the lifecycle is at least that particular state. We have an optional context here, and what we can do is, if it's empty, we don't do anything. We call this function, and then if we want to do this collection in a particular context, then we wrap it in the with context, and that's it. We don't have to do anything else. Okay, 5 minutes left. Let we go. So lastly, hopefully, we've learned the low-level APIs that we are using. Some of them might be familiar to you, but I think it's important to understand how, we spent a fair bit of time explaining repeat-on-lifecycle, but once the foundation is created, it was very easy to create other APIs on top of it, right? Like the foundation work was already in place. So when we think about how to build good APIs, I think repeat-on-lifecycle is a pretty good one that we can learn a lot from. And when it comes to good design, it's like we need to be compliant with a structured concurrency, right? We will see in a second that is really important to make sure that errors and cancellation signals are propagated properly. As we have with the repeat-on-lifecycle, if it's a really good API, it could be, serve as the foundation for other APIs and for other people to build on top of. And then we have to make them explicit and safe. And I think we are going to get all of that if we follow the previous steps. We will see in a second why something might not be safe to use. And then I think on a personal level, they also provide educational value. Like if you read the source code of APIs that have been created out there, or if you read the source code of Jetpack Compose, for example, you are going to learn many, many things out of that. So this is kind of things that I consider that could make a good API. But I'm going to show a counterexample of something that we actually did. The not so good design is this @repeating-job API. And this actually shipped in the first versions of alpha when the rest of the APIs that we saw. Repeat-on-lifecycle, we had repeat-on-lifecycle, flow-with-lifecycle, and this not so good @repeating-job that we ended up removing. Why is this not a great API? Well, if you see @repeating-job, it's amazing, right? It saves you from writing one line of code. You don't need to create a coroutine and then call repeat-on-lifecycle. And actually, if we look at the definition, this is actually what's doing. It's creating the lifecycle scope.launch and then calling repeat-on-lifecycle. So it's good because you save one line of code. But then things can get dangerous, and that's why we ended up removing it. So imagine that here you create a new coroutine in onCreate, for example, and then you do some init work that could be suspend function to initialize a few things. If inside this block you called @repeating-job, and again, this could easily pass a peer review, right? Because I'm doing some init work, and then I just want to start collecting from location updates, and I'm going to be updating the map. The disappointment comes when if you attempt to cancel job. If you attempt to cancel job, you might think you're going to stop as well the collection, but that's not true. And that's not true because @repeating-job, it's creating a new coroutine. And because it's creating a new coroutine under the hood, and you weren't aware of that, most likely, then it's not preserving the calling context, and the cancellation is not going to propagate down. So even if you think this is a very nice API, but this is not respecting structured concurrency, and that's why we ended up removing it. So yeah, this is something that we learned along the way, and we kind of stepped back and rethought what we wanted to do. That's pretty much it. I have 2 minutes left just to remind you of some resources in case you are curious about these APIs, you want to learn more about them. We have some good articles about that. Another reminder, don't forget to vote. A happy Cody is a happy Manuel, so smiles everywhere, everyone is happy. And then some takeaways that we can learn from this talk. Apart from bringing many adapters to a conference, which is always a top class insight here, every layer of your architecture should just do the right thing, right? You should just do what are the responsibilities, what they are in control, and you don't need to care that much about what's around you because things can get a little bit complicated. So if you do the right thing all the time, you have nothing to worry about. Then, obviously, this is the point of the talk, collect using the Lifecycle-aware APIs. You've seen it's quite easy. Jetpack Compose, just use the collectAsStateWithLifecycle, also available in Compose multi-platform, so why not? create good APIs that comply with structured concurrency. That's really, really, really important. And then if you want to keep learning, definitely reading source code written by others. And then, for example, from the library as well, that's, there are many gems inside that you can learn from. Thank you so much. We don't have time for questions, but I'm going to be around. It was great to meet you all. And yeah, thank you so much for your time. Thanks for coming.